Good morning. Wednesday, March the 15th, 2023. This is Allan Lind Jensen trying to solve problem 6 of section 5 of chapter 2. Now we get into the next space, and there's a little preparation in A. I prepared it by instead of doing these tedious calculations, which I may even do wrongly, I decided to do it in Maple. So the 1 point omega defines m, the inverse, and then transpose it. So we have the dual, which I copied here. And that means the dual space or dual lattice we shall show that L as a lattice and this tries the different what I usually consider the different, we'll just have to check that first, and then we can use this definition afterwards. That omega, that's an extension of the rational numbers with this polynomial, and then the different and that's that's square root 3/3 times I. Nope, square root 3 times I. So, and then it's not even that, it's the ideal. So the different is the ideal generated by this guy. And then when we multiply this by omega, we get 2 omega squared plus 2. I'll just do it. And this is minus omega minus 2. This, it's not nice. Well, let's just leave it up with the first thing here. And that was as far as it would go, all right. Now let's use the definition here. So an integer a plus b omega times, and that's L we shall use, so that's times 1. The trace of that is 2a it's the real part, so we have a real part here. It's 2a minus b times minus omega minus 1. And that's minus 1/2 so it's the sum of that and the complement. So the trace of omega is minus 1, so it's minus a plus b, and the trace of minus b is minus 2b, so it's minus a plus b. So let's just do this one again. The trace of, yeah. So we need these two to be integers. And subtracting them gives 3a is an integer. And adding them, 2a minus b and 2a plus 2b are integers, so that's just b being an integer. So that's the lattice I see is that it's spanned by 1/3 and I. And can we do something here to reduce it? We can actually I'm not sure how to reduce this. And I can't see that this being rational, I can't see how we can get square root 3 into it at all. So it's break time where I look at this. The first thing I did in the break was to look up this definition that I found in Koch's book. I've shown it before, Helmut Koch on number theory, and it's defined as the dual ideal, which is a fractional ideal. So this is the dual ideal of all of the integers, which turns out to be a fractional ideal. But we have already used the term dual in problem 5, so what should one call it? But that did confuse me somewhat. Next, I'm actually applying what's like high school technique here. We need to write L mark as a lattice in coordinates of 1 and omega. And the same with this lattice. We need to solve the write up the matrix generator in those coordinates, as I've already started. Then I would like to draw it just to make sure that this is only, I didn't finish it correctly, of course, but when I have a matrix representation of the lattice, then another one can be made by multiplying it with a matrix of determinant unity. So that way we can manipulate it in a sense that's more like a more professional. I'll do that not online, not while recording. I'll do that and then present the result. Unfortunately, I lost the recording, it failed, of my solving part A of the problem. I checked Helmut Koch and Kohn's books on algebraic number theory and found that the basis was called the dual basis, but the ideal was called, also in this book, the complement or the complementary ideal. So it seems that dual is used for the basis, and for the module we use the word complement. I didn't realize at the time that I could compute the complementary ideal just by solving the linear equations. The trace here used on a basis for the lattice actually gives n linear equations for solving the dual basis. I didn't realize that at the time, but working with problem A, I found out how to do it. It's quite elementary, of course, just like it's done in the book, finding the matrix, its inverse and its transpose. So that was very nice, because now I'm able to find the inverse of an ideal in any number field, and I wasn't able to do that otherwise. But the recording of finding this method was lost, unfortunately. Therefore, we just skip to the next part. Hello guys, it's been a week or more since I finished problem A. Actually, Tuesday I was ready to start working on part B, but then it occurred to me that this meant some more to me than just solving problem A. There was some deeper significance to this, to being able to solve the problem. Now, the next night I got otolithis. Some of the crystals in my inner ear got stuck where they really shouldn't have been stuck. It was both ears, and I was vomiting my guts out. Fortunately, it can be treated today very easily, and the next day my physician cured the one ear, and then the next day I visited the doctor having to do with the ears, and there I was treated for the other ear. So it's really a miracle. It was treated within 40 hours or even less, which is a miracle. So I was very tired afterwards, but now I'm ready to report on what solving this meant to me, and maybe start on part B of the problem. Now, the point is that I was able to solve this using linear algebra. And I thought a little more about it. And one of the books I've used for Galois theory, this Bastido's book on field extensions. And I've just quoted two theorems from it. Dedekind's independence theorem, where the maps one-to-one from E to F, they can be considered as given a linear structure by multiplying by elements of F, and as such they form a linear independent subset. There's a nice proof by Artin. He worked on proving the elementary theorems of field extensions using linear algebra, and that has made it much easier for students since then. So a genius who also tried to make things easier for students. Respect. The next is, if L is finite and separable over K, then the trace map is non-trivial. It's the sum of all the monomorphism of E into some, or into the algebraic closure of E over F. And those monomorphisms are independent, so the trace map must be non-trivial. And of course, if we take an element in the base field, then it's just the dimension of L over K times alpha, so that's trivial. So it's only if it's non-separable we can have a problem. The next book where I had the problem, that was this book by Koblitz, no, by Kuhn, sorry. And I took a picture of the main preposition where he the complement here is defined exactly exactly this way. That's the complement. So, and it's, so to speak, the reciprocal of the different. So they call it the complement, but maybe the names are not standardized. I don't know. Well, so the idea is that if L is n-dimensional over K, then we have a basis, and then we can consider the map, that an element is mapped onto the trace with each basis vector. This is n-dimensional over K as well as K to the nth. So we can ask, what is the kernel of this map? And if these traces all vanish, then the trace of any guy will vanish, particularly the reciprocal of x. So if x is not naught, then we can take the reciprocal, and then we get trace 1 equals naught, which is a contradiction. So that means that this map has trivial kernel, which means it's invertible, and it's onto, and it's a linear map, so it can be represented by a matrix, and that matrix will have an inverse. And that was the point I missed when I studied this section of Kuhn's book many years ago. And this is why this is such a breakthrough for me, because this is the matrix representing This is the matrix representing this map, and that makes it possible to compute the complement. And the discriminant, of course, is given by, no, the different is given by the ideal generated by the derivative evaluated at the element. So that's easy, but that means that we can compute the inverse of any ideal or any ideal by first finding the complement, which is done by linear algebra, and then multiplying by this element. So that's what it means to me to be able to find this method, that I'm now able to explicitly compute the inverse of any fractional ideal. All right, now we can start on part B. I've written the formula from problem 5, which I believe we must use, and we must use it on this formula. I'll just put myself over in the corner where I belong. There we go. So that is, we have a black F let's call it X. Because it has two components. So, and now it's been a week, so I've forgot what the Fourier transform of this is. We call that Y. We also have to sum over another lattice. So yeah, I'll just make a break while I find that. It turned out to be what I hoped it was. Now what do we have to do? Yeah, we have to be able to do this anyway. So we can just as well do it. And then we have to yes, I don't know what we have to do. So let's get on with the show and take the Mellon transform of F here, or rather the sum. The zeta function, I'll just have to look up the definition to check whether we shall use S or S halves. The definition is in problem 1, and it seems we shall just use t to s. And as usual, we change integration and summation, and then find out later when it will work. And what are the conditions that it holds? I forget this, so we just have to do it again. We sum over the plane, and that is, we have the sum over r to some power minus 2s, and then r dr, so that's r to 1 minus 2s. It's dominated by this integral. So it's like r to 2 minus 2s from like 1 to infinity. So we need this to be negative. And that means s must be larger than 1, and in general it's the real part of s that must be larger than 1. So that's when this will converge. Oh, then we are home. This is exactly pi minus s gamma s, the zeta function. And now I have really been stupid. I knew this, so I'm not quite fresh yet. You see, this actually, before being able to make the Mellon transform, we need to ensure what happens as t tends to infinity. And what happens here is that naught gives unity. Oh my God, that's really silly. So we have to, it's actually much more complicated than I anticipated first. And the worst thing is that I knew this a week ago. Hello. 29th of March, so it's been a fortnight before the last recording. I've had a lot of days where I could work on mathematics, like 1/2 hour up to 1 hour, and then I practically did nothing. Now I guess I'm ready to carry on with the problem 6. I spent some of the time working on well, what did I work on? It was actually extending problem part A. When I solved it, I wasn't aware here that the lattice had to be real. You can see, so there was some confusion there. And I felt really wrong about having complex numbers as I've thought here. So I spent the time trying to work out the general case. If we have a number field q extended with square root n, is it possible to make a real lattice that agrees with the norm? And one solution I found was this lattice. So this is the norm map into the rational numbers, and the norm is defined this way. And of course g is square root n if n is equivalent to 2 or 3 modulo 4, and n must be square root free, of course. And if n is equivalent to 1, then this is the norm, and g is 1 plus square root n halves. Yeah. And with the less lattice, we just need to verify we've got the right lattice. But the next thing I noticed was that it doesn't work when n is negative. Well, first of all, this solution gives, in that case, here we get imaginary numbers, which I didn't like. But there is a more important fact. If we want to sum over some lattice, then if n is negative, then the number field has 1 units. Like if n is 2, then we have the unit square root 2 minus 1, which has norm minus 1. And all powers of that unit, they have norm 1. So it's an infinity of points having norm 1. I don't think they form a sublattice, so it could make the quotient. So it doesn't work, I believe, summing over all the points in some lattice if n is positive. The next thing is that if we have to sum only over some lattice, then if this is the lattice of integers, then we don't get all the ideals except when it's a principal ideal domain, and that means that the class number must be unity. So that leaves us with very few or very rare occurrences, but -1, the Gauss integers, and -3, the one of this problem, are exactly covered by it. And we need to verify that the norm of A plus GP actually is equal to the inner product. And in this case, where n is equivalent to 2 or 3, it's quite obvious, a squared minus nb squared. It's slightly more difficult when n is equivalent to 1. It's a times this plus b times this. That's what we get, a and b. And then this one squared and the other one squared. These two guys add up to a squared. And this should be ab, little mistake. And then 1 minus n fourth. So that's just an algebraic verification. How about the dual lattice? So the discriminant is square root minus n halves, so we can find the dual basis easily. And then I want to find the scalar product here of a vector with itself. What does it give? So it's a times this guy plus b times this guy, or this vector. And then we compute it and end up that it actually gives 4 divided by minus n times the norm of b minus ag, which means that we can sum over the original lattice, but the results have to be changed so that n is -3, then it's 4/3. And this, of course, is also a start here, because we have to solve this before we can do this. before we can make the integration. This is summing over our lattice. That equals, now m to minus first, that's 2 divided by square root 3. And then we sum, and then the Fourier transform of this is 1 divided by t, which we can put out here. And then we sum over the dual lattice. But it's the same if we sum over the lattice. And then this scalar product was, I have to look it up, 4 divided by 3. So let's compare. That was exactly what we should prove. So let's call this theta of t. Null lies in the lattice, so that means that as t tends to infinity, this function has fast decrease. And then this can be written as 2 divided by square root 3 theta of 4 divided by 3t and that means that 2 divided by square root 3t theta of 4 divided by 3t minus 1 has fast decreased for t tending to infinity. And that means that what does that mean? Oops. That this guy has fast decrease for t ending to infinity, and taking the reciprocal, or rather we change variables so that u becomes 4 divided by 3t. That means t equals 4 divided by 3u. So square root 3t halves equals 2 divided by square root 3u. this is just square root 3. Never mind. It will be eaten anyway when we have fast decrease, so. But I need to get away with t. So t is 4, 3u. Oh, that's the reciprocal. So it's just square root 3u halves times theta of u minus 2 divided by square root 3u has fast decrease as u tends to naught, and that means that this guy in itself has fast decrease. So now we can define our lambda function. That means that if we are well, let's do it as I think we should. We like the melon transform from 0 to 1. And from unity to infinity, this is an entire function. So the next step is to see if for S being sufficiently large, we can actually compute it. And when S is larger than, when S is positive, we can integrate this into 0, separate them. And when S is larger than -1, or the real part of S, and that means for the real part of S, we can actually, being positive, we can actually take this integration by part. And of course, exchanging integral and sum will require that the real part of S being greater than 1. I think we've had that before. So we get the integral from 0 to infinity of theta. Minus the integral this must be done to infinity. So this one works when the real part of S is larger than, we need to go larger than 1. And this will work when the real part of S is negative. I had really hoped that there were some strip where we could do this. This calls for a break. I read the section on the legacy zeta function again and realized that what we have to do was to take the x equals naught out of this sum, and that means that we always sum over all except x equals naught. So it's a little more complicated than I thought. How do we do that? We could define a new function which excludes. Yeah, I'll just put a bar. How do we do that? Zeta star t plus 1 minus 2 square root 3t t to s dt minus t divided by t plus the integral then we can perform the integral from naught to unity as long as the imaginary part of s is larger than unity. Again, excluding the center. And then we have to look at the definition of theta. It's pi to minus s gamma s, and then 1 divided by x to 2s plus, and then this is 1 divided by dt, 1 divided by s minus s minus unity. And this equals the L function. What was it called? Zeta k, all right. Plus 1. And that means that zeta k of s equals, and this being an entire function and 1 divided by gamma being entire, the pole at s equals naught vanishes, so we have a pole at s equals 1 with residue equal to minus 2 divided by square root 3. And then we have zeros at the even negative numbers, excluding naught, of course, only the even negative numbers. So we have solved B, and we have solved C. I have a little time this evening. In the afternoon I played bridge, and soon I have to go to tennis, but I've thought a little and I just wanted to report that. The first thing is that this +1 is insane, because the sum we get here is exactly the sum, except we don't sum over naught, which we shouldn't. We should sum over all distinct from naught. So that needs to be taken away. That's it. And then when I read the problem, the text, we should also derive a functional equation, which I forgot all about. I also have an idea how to go on, but let's just derive the functional equation. And now what do we do here? I think the right thing is to use the transformation formula, which we have where do we have that? Z of t equals this, and then change variable afterwards. So it's we just forget this. So I've already forgot it. 2 divided by square root 3 t theta of, and the same I believe, 4 divided by 3 square root 3, right? 3t, of course, yes. Minus and the other integral from 1 to infinity. And then we must make a change of variable. We set u equal to 4 divided by 3t. Meaning du d per t equals minus, now what's that? Du per u equals minus dt per t. Yeah, the constant cancels. All right. Oops. now we go from not that's infinity, but 1 when t is 1, u maps to 4/3. So I'm actually back to doing this again, getting some new functions here. So I have to do all this again to get the exact result. And I won't do that on the tablet. I'll do it by hand and then show the result. Or do it on a sheet of paper twice and then show you the result. We will get a reality check in part E. And the idea I got over here was to use the product formula. The theta function of k is the product of overall prime ideals and then we have primes that are inert, and they come as a factor 1 divided by 1 minus p squared, or whatever it is. That was in the Gaussian case. Yeah, here the norm should be p squared. Yeah, and then those that split, their norm should be p. So that's the inert, and then split. They should come like this. So that's the product, the inerts and the split. And of course we have 3 which ramifies. I don't know what happens to that. I expected that would be 1 divided by PR. That's 1 minus 3 to minus s. But we'll just have to check about that. So the idea was to work on the product formula and then make the series expansion and see what signs would come. But that's just an idea. I haven't started working on it at all. Well, that was what I would show you tonight. March the 30th, Thursday. I stopped here because I thought that was getting a little complicated, or felt it was getting a little complicated. And I have done some work. Maybe we should maximize that. First, I repeated the calculation. I hope you get a clear picture. But I thought that it would be simpler just to use the reciprocal. So that's the calculation I made here. And then I checked it by computing the residue. And I got minus 2 pi divided by square root 2. Not what I got here. And we multiply by s minus 1 and let s tend to unity, then we get a factor pi here. So that means pi should be in the, and that's because it's pi to minus s here. So there's another mistake here. It should be pi to minus s. So we get a pi up here. And that means that I did get the reciprocity relation. So I have copied it now. And so this equals that. That's the, it seems like it may be symmetrized some way, but I don't really know how to do it. So this finishes questions part C of the problem. Now let's try to work on my idea on problem part D. The prime ideals. And therefore we must find out how the primes factor in Q extended with the root of the polynomial x squared plus x plus 1. The determinant is minus 3. So minus 3 will ramify. So that means that, and it's of course square root minus 3 times I. And what's the norm? That's 3, of course. Two is inert. How do I know that, really? So it has norm 4. And then comes 5. How do the rest of the primes factorize? So the question is whether the prime is a square modulo 3. Why is that so? No, whether minus 3 is a square in, there we go, minus 3 must be a square modulo p. So that's the answer to that. And it's minus 1 p 3 over p. And if p is equal to 1 modulo 4, then this gives plus, and we may reflect this. And if p is equivalent to minus 1, 3 modulo 4, then this gives minus 1, and we must change sign. So this holds. We've had that before. And that means that it's minus 1 if p is equivalent to minus 1 modulo 3, plus 1 if p is equivalent to 1 modulo 3. And that means that 5 we are here, it's inert. Seven splits. So there are two ideals with norm 7. So it's squared. Etc. And I got an idea here, which is to take the zeta function itself, which is the product of a rational primes, we've got that in every factor, and then let's see what's left. Here's 1 plus 2 to minus s, nothing. 1 plus 5 to minus s, 1 divided by 1 minus 7 to minus s. And you can see the system now. If the prime is equivalent to 1 modular 3, or we rather just get this symbol, I forgot the zeta function for the rational numbers. Let's just put a q on. And this is exactly the L function of the character modulo 3. So I really thought I would never be able to prove that. I've seen it at least at Wikipedia and said, wow, can one prove that? It's actually accessible for humans as well. Right. To do the last part of the problem, part E, I need to write up the reflection formula for the zeta function, the rational zeta function, and the L function of the character P over 3, or N over 3. So I'll do that, and then I'll find the reflection formula. Then I'll make a break where I compare them, and then I hope that I'll be able to find the final truth and make the two expressions agree. I have written the two formulas, and we just need to multiply the left-hand side and right-hand side, and we get the result. We need to compute g of chi. We have done that before. It's the character of order 3, so it's chi of 1 times omega plus chi of 2 omega squared. and omega squared is minus omega minus 1. So it just gives square root 3 times the imaginary unit. And that means that n to minus 1/2 g of chi just gives I. That's weird. I don't think I found any imaginary unit here. Well, let's take one step at a time. If we, in this guy, set s equal to s minus 1, then we get this. And if we set s equal to s minus 1, then this gives this, 1 minus s, that's 1 minus s halves. So this is nice simple symmetry. But I'll just use the function for the gamma product, square root pi. They'll come on both sides, so we'll just neglect that. And then 2, and it's s halves. Square root pi cancel. And the smaller one is, the smaller one is, 1/2, and then we must substitute I think we should do the substitution explicitly. This is the larger, so we substitute s with s plus 1. That's easy. S plus 1 all the way through times 2, and then minus 1 minus s, then gamma of s minus 1. Now that's weird. Shouldn't it rather be 1 minus s? Yeah, s is substituted with 1 minus s. Then it's 2 to plus s. And gamma of 1 minus s and that means if we define I really hate this imaginary guy, so let's look at the formula again. Here we have it minus I into minus s. So I miscopied. Minus I. So I times I gives plus 1. All right. There we go. That makes sense. If this is it, then the formula simply states this. Wow. That seems more simple than the one I arrived at. Particularly this square root 3 annoys me, because there's not much square root 3 here. So can we get away with that? Well. I'll have to look at it at my leisure while I'm having a cup of coffee. I've gone through it all again, and I believe I have reconciled it, though I haven't done the final details. The first thing I noticed was that this is all right, except that here I changed the sign. No good. And then, of course, this parenthesis is confusing. But that's gamma of s. Next, when we make this the right change, just taking the reciprocal, oh, I haven't done that, I just showed it to you. Well, I did it once again, so I'll just show it to you. So there we go. And you can see the parts. We get the same ones at the end here. I've just interchanged 1 and s, so that gives the minus. You couldn't read the constant, I think. I'll just write it. All right, here we have the formula. These parts agree. So we are left with pi to minus s, gamma of s, zeta k of s equals 4 pi third to s minus 1, gamma of 1 minus s, zeta k of 1 minus s. And then we would like to symmetrize this so that we have it well. Now we have the other formula here, and it appears that I misread it. It says n to minus s. So it should be n to minus s. And that means we get 3 to 1/2 minus s. and that should be, yeah. No, yeah, and then I times I, so it's 3 to 1/2 minus s. Now where do we write that? Oh, I didn't write it at all. It should be on the right-hand side here. So if we multiply with pi, with square root pi, and divide by 2, the power of 2 here, what do we get? So first 2 to s minus 1, then 3 to 1/2 minus s, then pi, we multiply by pi to 1/2, so are we getting any closer to what we have? Pi to s minus 1, that agrees. And then it seems that we should have taken square root of this at some point. Well, I've not quite finished, but I will stop the recording here and just do it by myself and not report it. As you see, we are quickly converging towards something. Before going to tennis, I just had a little time to work at it, and I believe I've solved it. And this is the function, and this is the symmetry relation. And I've made both this and this into this form. So that's it. Problem 6 successfully ended after weeks of not being able to think very clearly, but now I'm up to it again.